Okay, I guess let's get started. We're very happy today to have Ben here to tell us something about proving the weak gravity conjecture in perturbative string theory. Ben, is all yours now.
All right. Thanks very much for inviting me to give a talk. And I apologize in advance for showing you my bad handwriting rather than nice slides. I also have too much material to talk about, so I'm going to try to skip certain parts. So don't get it. If you want to hear more about something, then stop me and I'll go back. So what I'm going to be talking about is a recent paper with my former postdoc, Matteo Latito, and also work in progress. So our recent paper is about proving the weak gravity conjecture in perturbative bosonic string theory, and the work in progress is about superstring theory. What I'm going to talk about today is mostly about bosonic string theory, but the things that I'm going to talk about will generalize just with some technical differences. That's something that we are currently working out. Hopefully we'll finish within the next couple months. So first, let me start by talking about the weak gravity conjecture in general, and then I'll come to our proof. So the weak gravity conjecture, which I guess at this point is almost 20 years old, is the statement that in any theory of quantum gravity, if I have a massless photon, there should be a light-charged particle where, well, light is maybe in parentheses, but that's what Kerman says, where the charge to mass ratio should be at least as big as the charge to mass ratio of a large extremal black hole. So what do I mean by extremal here? I mean that the black hole is the lightest it can possibly be given the charge that it has. Right, so its mass is the infimum of all the black hole masses of that charge. And the large here, well, maybe I'll come to that in a second. When the cosmological constant is 0, this extremal mass scales linearly with charge when the charge is large enough. So that's what I mean by large, is I'm looking at this ratio in that large charge limit. If I don't look at the large charge limit, there might be derivative corrections. Okay. So we have to have some particle with this charge to mass ratio that's at least as big as this large charge limit of the black hole, extremal black hole charge to mass ratio. I'm going to call that super extremal henceforward, so I don't have to keep saying all this. And what does this mean? That means that heavy extremal black holes or nearly extremal black holes are unstable. They can always decay to this particle, many copies of this particle, right? They can give it off, they can radiate, they can maybe even decay in other ways, but kinematically this decay is allowed. They might be marginally unstable in certain cases, like if they're BPS, which just means, the decay would have 0 energy. In other words, I have to excite the black hole very slightly in order to make the decay possible. But the threshold that the amount of energy I have to add to make the decay possible is, infinitesimal. It can be as small as I like. Okay, so the black holes have to be either unstable or marginally unstable. Okay, that's what the conjecture means. That's just a restatement of the conjecture. So if I don't put in this this caveat that's not in the original paper about the particle being light, you could actually imagine that the things that fulfill the conjecture are black holes themselves. This can happen if the derivative corrections to black holes make their masses be lighter when the charge is smaller, right? So, as I said, asymptotically, this is a constant slope, but then the corrections might bring you down a little bit as the charge is smaller. This is one way that the weak gravity conjecture could be satisfied. It's actually not very well tested, even in string theory, how often this happens. It's an interesting research problem, which is one of the things we mentioned Muldrow a minute ago, one of the things that Muldrow is working on. But that's not what I'm going to focus on today. Okay. So why should black holes be unstable? There unfortunately isn't a really compelling bottom-up reason that this should be true. It's really an observation that we look at lots of different string theories, and this is always true. There is a heuristic motivation, and the heuristic motivation has to do with the idea that there should not be global symmetries in quantum gravity. So let me rehash that argument. The argument is if I have a global symmetry, which is different from what I'm talking about with the weak gravity conjecture. Now I'm plotting the mass of the mass here and the global charge. Then through gravitational collapse, I can make heavy black holes with as much global charge as I want. I can throw, say, a bunch of baryons. If the global charge is baryon number, I can throw a bunch of baryons together and I make a very heavy black hole with as much charge as I want. And then I let these things decay. But because it's a global charge, you can't tell outside the black hole that that black hole has that charge. And the Hawking radiation, therefore, is not going to preferentially give off baryons versus antibaryons, and it won't discharge as it decays. So what you're going to end up with is a situation where you get these black holes with arbitrarily large global charge, whose mass is close to the point, close to, say, the Planck scale, where your Hawking radiation calculation is no longer valid. Or maybe it's a little bit above the Planck scale, but at some point, whenever your calculation breaks down. Sometimes people call these things remnants. Now, what happens to these things at that point is maybe a little complicated, but they can't just decay back to this, original global charge particle that I had, because that's kinematically not allowed. Maybe the sharpest reason for not liking what happens here is if you look at any scale, say, above this point where the Hawking calculation breaks down, then the number of different black holes of a given mass is infinite, because they can have arbitrarily large global charge. So that means you have an infinite, number of microstates, and that doesn't make sense with the Bekenstein-Hawking entropy formula. So this is a pretty bad contradiction, and so it's maybe it's one of the best reasons for believing this statement that there's no global symmetries in quantum gravities. There's other arguments that by this point for the same thing. Okay, so let's talk about a gauge symmetry. If you have a gauge symmetry, this changes a little bit because now there is an electric field. So maybe the gauge coupling is very small, but still, if you throw in enough charge, you'll see the electric field. And the electric field also affects the black hole geometry at some point, right, because of this extremality bound. So what happens when you do the same process, you make this charged black hole and you let it decay, is that as it gets close to extremality, the behavior may change. It may start to discharge. Now, what happens in the end, it doesn't necessarily discharge very much if the charged particles are heavy, because it likes to produce massive stuff. That's the easiest thing to produce. What happens in the end depends on whether the weak gravity conjecture is satisfied. Either you just sit here, or if the weak gravity conjecture is violated and you get these stable black holes, or you decay by some Schwinger effect by emitting pairs of particle antiparticle of these things that are super extremal. Okay. But again, there's not an obvious reason why you couldn't just have these stable black holes that just sit here. So there's some connection to global symmetries. There's more connection, which I'll mention later, but there's not an obvious reason why the weak gravity conjecture has to be true from the bottom up. It has, however, been checked in many examples in string theory. One prototypical example I want to show is that if heterotic string theory on a torus, the mass formula for the string modes looks like this. I have some left moving charge, some right moving charge, some left and right moving oscillators, which are integers, and the way I'm writing the formula. The number of left moving charges is 16 more than the number of right moving charges, right? And the charges sit on this lattice, which is even self-dual. And all these even self-dual lattices are related to each other by what you call like a Lorentz transformation on the lattice. The boost part of this Lorentz transformation actually changes the string theory because it changes what's the left-handed part and what's the right-handed part. So they really have a moduli space, which is this coset of the whole Lorentz group divided by the rotations. And then there's other discrete quotients that I'm not writing. Okay. And then you can figure out what the extremality bound is. This, goes way back. And the extremality bound is just this simple statement: alpha prime over 4m squared is bigger than a half maximum of the left and the right moving charge squared. And you can compare that with the lightest state. And what you see is that the lightest state is always at least as light as the extremality bound. So indeed, the lightest state for every charge is super extremal. It might be exactly extremal in some cases when the right moving charge is bigger than or equal to the left moving charge, and otherwise it's strictly super extreme. So the weak gravity conjecture is satisfied. You'll notice that in this example, sometimes it's saturated. And also note that these string modes are BPS when the right moving oscillators are not there. So this is the BPS bound. So in some of these cases also we have the lightest particle of a given charge being BPS. That's when Q right squared is bigger than Q is at least Q left squared minus 2. So slightly different condition than when you get this exactly extremal thing. So I can divide into 3 cases. One is when Q right squared is at least as big as Q left squared, then both the extremal black hole and the lightest charged particle are BPS. And we have the weak gravity conjecture saturated. And in fact, when the extremal black hole is BPS, there's no way for the extremal, you can only saturate the weak gravity conjecture, right? Because nothing could have more charge to mass ratio than the black hole because it's BPS. Then in this special case where Q right squared is Q left squared minus 2, the charged particle is BPS, but the extremal black hole is not. So the weak gravity conjecture is, in this case, satisfied but not saturated. This is an important proof of principle that when you have, it's not always true when you have BPS particles that they saturate the weak gravity conjecture. They can satisfy it with room to spare. And in this other case, when Q right squared is less than Q left squared minus 2, then neither the lightest charged particle nor the extremal black hole is BPS. But the weak gravity conjecture is still saturated, it's satisfied, it's just not saturated. Okay, so Uguri and Vafa later add this addendum to the weak gravity conjecture, which is that the weak gravity conjecture can only be saturated if the super extremal particle is BPS. This kind of makes sense because, you know, if you have some inequality that you're saturating, you might expect that corrections are going to mess that up. But only in the case when the particle is BPS, then it doesn't get corrected, right? And then you might expect that indeed it can saturate the bound. That doesn't mean BPS, so right, being BPS doesn't mean you have to saturate the bound, as we just showed. Okay. And then the other observation that I want to make about this example is that there's a lot, not just, you know, a small collection of super extremal charged particles. There's a lot of them. There's at least one for every possible charge on the charge lattice. So this example satisfies this criterion called the lattice weak gravity conjecture criterion. It was once called the lattice weak gravity conjecture, but it turns out it's not always true that you have a super extremal charged particle of every possible quantized charge. So an example where that doesn't happen can be constructed, say, taking a compactification on a 3 torus with a particular kind of orbifold where you shift by a half period vertically, and then you do this reflection diagonally in the horizontal directions at the same time. So it's this translation and reflection combined that gives me this orbifold. This is a fixed point free orbifold. So even without thinking about the details of the string theory, you can find the light spectrum even just with E of t arguments. And what happens with this orbifold is that the graviphoton gauge symmetry, which would have been U1 cubed from the torus, becomes U1 squared. And I have KK modes with KK numbers for each direction on the torus. And the sum of N1 and N2 is the charge under one gauge field, and N3 is the charge under the other. And I can form invariant wave functions with these KK modes. The details are not too important. So now I have this normal kind of KK mass formula. And I can choose the radii to be, for this first 2 directions to be equal so they don't break the Z2. And you can compare the extremality, the extremal mass with the mass of these KK modes. You can take the difference, compare them. You see that the lightest KK mode is extremal if N1 equals N2, and otherwise it's not. So if N1 and N2 are not equal, then it's not extremal. If you go back and look here, you see that if N1 and N2 are equal, then this charge has to be even. Right? So I get these things at even charge that are extremal, but when the charge is odd, there's no way to have N1 be equal to N2. And so I don't get anything that's extreme. So in this way, I don't get any super extremal particles with odd charge. And you can check if you put this in string theory that the conclusion doesn't change, right? This kind of Kluver-Klein analysis is telling us the whole story. So what that means is that in this kind of example, there's a finite index sublattice of the charge lattice where there's a super extremal charge particle everywhere on that sublattice. This is the refinement of this kind of lattice statement, and this seems to be true in all known examples, at least in bigger than or equal to 5 dimensions. There's an interesting caveat in 4 dimensions that I won't go into, having to do with loop corrections. There's a weaker statement, which is just saying that you have an infinite tower of super extremal things in every direction in the charge lattice. And this is interesting because it can be, quote unquote, derived from the requirement that after you take a given quantum gravity and you put it on a circle, and you look at just the mild weak gravity conjecture, just the existence of a single super extremal charge particle in a given direction. In that theory, then you can derive this tower statement. That has to be true in the higher dimensional theory to make the mild weak gravity conjecture true in the lower dimensional theory. So that's interesting. The thing I'm really going to focus on in this talk is this sublattice conjecture because it comes naturally out of string theory. It's a little stronger than this statement, but they're closely related. Okay. Something to note is that with either of these conjectures, you have a tower of particles that's starting at a mass scale that's related to the gauge coupling. So in 4 dimensions, the mass scale where the tower starts is the gauge coupling times the Planck scale. And there's a similar formula in other dimensions. What that means is that when you take the gauge coupling to 0, you have an infinite tower of charged particles that's becoming light. And that's going to change your low energy theory. In a sense, what you have here is the quantum gravity resisting the limit where you take the gauge coupling to 0, which would have been the global symmetry limit. So you see there really is a connection between the weak gravity conjecture, or at least these stronger forms of the weak gravity conjecture, and the idea that you should not have global symmetries in quantum gravity. It's a little bit more subtle to see than this kind of naive arguments about remnants, but there is a connection. Okay. So what's the evidence for this sublattice weak gravity conjecture? You can make very general arguments that it works for Kaluza-Klein theories with KK photons, like I mentioned an example of above. There's a partial existing proof in tree-level string theory, which is the thing that I'm going to complete today, which uses modular invariance. This goes back to 2016 to show that there's a finite index sublattice of the charge lattice where you have particles with this mass. Remember, we saw this mass formula before for the heterotic string on a torus. The reason this is a partial argument, so it gives you this whole sublattice of charged particles with m proportional to q. But the reason this argument is not complete is one hasn't figured out what the extremality bound is for the black holes. You have to compare this with extremal black holes in order to see if these things are super extremal or not. So that's not something that we knew how to do in 2016. And so we weren't able to finish that part of the argument. We just showed that we had this tower. You can check in some, say, orbifold examples that this is indeed, these things are extremal. But you can have many more general string theories, string compactifications where you can't check that. Okay. I should say that
Ben, sorry, before you go on, I've got a quick dumb question.
Yes.
Looking at your remarks about how the extremal depends upon moduli, are there any general statements about moduli dependence that you can make? For example, in a heterotic string compactification, the space-time superpotential is a section of a tensor square of the Bagger-Witten line bundle, essentially the Hodge line bundle over the Calabi-Yau. Is there some analogous statement that can be made here? Can these masses be thought of as sections of some line bundle over the superconformal field theory moduli space, something like that? Just curious.
I'm going to say something about moduli dependence when I get to our argument. So
I'll just wait for it then.
In effect, an important part of our argument is figuring out how the masses can possibly depend on the moduli.
Okay.
Because that's the reason why it's non-trivial to know what the black hole extremality bound is. If there were no moduli around, they would just be Royston-Nordstrom black holes, and that's a very simple gravity calculation to figure out what the extremality bound is. The presence of the moduli is the whole source of the complication, indeed. Okay. So if you just hand me a general effective field theory, I have to solve PDEs in order to find the extremality bound. So that's not easy. Okay. So that's why we didn't solve this problem in 2016. So what I want to do for the rest of the talk is I want to review this modular invariance argument, which of course is crucial. This really goes back to 2016, although in our recent paper, we've given kind of a more complete, better version of the argument. And then I want to show that this is actually the extremality bound in general. And that's a new result. And this is going to prove for us the sublattice weak gravity conjecture as a theorem. It'll not only prove this, it'll prove this Aguri-Vafa version where it can only be saturated for BPS states, which for this talk, we're talking about the bosonic string theory, so there's no BPS state, so it will never be saturated. And this is going to be at tree level, and the fact that it's never saturated is going to protect us against perturbative loop corrections because those are parametrically small, so they're not going to change this tree level result when the string coupling is parametrically small. This is only going to be for the electric NS-NS charges in the theory because that's the things under which the worldsheet modes are charged. We can't, for bosonic string theory, we could also have magnetic NS-NS charge, at least in 4 or 5 dimensions. That I'm not going to talk about. And of course, for type 2 superstrings, I could have RR gauge charges. I could also have open string gauge field charges. I'm also not going to talk about those. Okay. So, but before we go on to the details, I want to tell you, how do we show this extremality bound? How do we show this is the extremality bound? So we start with a seemingly unrelated point. We think about the long-range forces between particles, which if you write down your general effective field theory, you've got, Einstein-Hilbert, you've got moduli with some nonlinear sigma model, you've got gauge kinetic terms. And you can compute the long-range forces, the 1 over r to the d minus 2 component, which is the leading part. And there's this general formula like this. So it's a nice result. And then if this coefficient is non-negative, we call these things self-repulsive, which means that either the leading long-range force is 0 or it's repulsive. There's a analogous conjecture you can make where instead of talking about super extremality, you talk about self-repulsiveness. This is what we sometimes call this repulsive force conjecture. If you go back to the original weak gravity conjecture paper, they use both things interchangeably, but when there are moduli, these things are not the same. When there are moduli, being super extremal and being self-repulsive are not the same concept. So you should distinguish. But that's not really the main interest of the talk. That's the weak gravity conjecture. So why am I talking about this? There's an interesting fact, which is that a particle of charge q and mass m of phi, which is self-repulsive everywhere in the moduli space, is necessarily super extremal. This is an EFT theorem. How do you do this? You write the black hole mass as something which is non-negative, plus an integral of basically the long-range force here, plus, let me take w of phi to be some function, which you should think of as like the mass as a function of the moduli of a given particle. And then this would be the long-range self-force on that particle in that case. And this is just its mass far away from the black hole. And this is non-negative. So basically, if this thing is self-repulsive everywhere, then this contribution is also non-negative. It would have been 0 if this was 0 self-force. And so that tells you the mass of the black hole is at least the mass of the particle far away, or proportional to. I'm putting in factors of n here because the particle, I might want n particles to make something that has the same charge as my black hole. Okay, so that proves the statement up here with, of course, I'm skipping lots of the steps, but just telling you roughly how it goes, that if I have this particle which is self-repulsive everywhere in the moduli space, then it's super extreme. So what that means is instead of asking this complicated question about PDEs, blah, blah, to find the extremality bound, I can just compute the long-range force on my particles and see if they happen to be self-repulsive and that particle is present everywhere in the moduli space. Say that's the particle that I got with the modular invariance argument, so it has to be there everywhere. Then I can conclude that it's super extremal, and then I'll have closed my gap in my theorem. So that's the strategy. Any questions about that strategy before we go on to the details?
All good so far.
All right, great. So that's switch over here. Okay. Now I'm going to focus on bosonic string theory here. And like I said, the superstring, especially the heterotic string, is work in progress, which hopefully will be done with in the next few months. So let me first define what I mean by a closed-oriented bosonic string theory. In a flat background, that's going to have a worldsheet CFT which factors. There's going to be free bosons describing the non-compact Minkowski background and some internal CFT. And this could be, the nonlinear sigma model for some compactification, or it could be some non-geometric thing. Right? It doesn't have to be geometric. What I require is that it's a unitary modular invariant. I forgot to write compact CFT with the right central charges to make this critical string theory. Okay, and the physical states of this bosonic string theory are 1-1 primaries. And in particular, they're going to come from primaries of this internal CFT. And if you look at some of the possible primaries, these are the ones that can give you massless fields in the EFT. So if you have the identity operator, this gives you the graviton, the Kalpermon 2 form, and the dilaton in the total theory, right? The polarization of these states is coming entirely from this free boson stuff, right? So for as far as this internal CFT is concerned, this is just the identity. You have 1-0 operators in the internal CFT. These are conserved currents. That gives you gauge fields. Similarly, 0-1 right-moving conserved currents also give you gauge fields in the EFT. And then 1-1 operators, which are marginal operators in the internal CFT, will give you massless scalars other than the dilaton. Note that these are marginal. If they happen to be exactly marginal operators, then these are going to be moduli, these scalars, right? Moduli means that the tree level potential is exactly 0, as opposed to just having 0 tree level mass. Okay. So in general, if you have some other weight primary in your internal CFT, then you're going to get some massive states in your EFT. And that's, of course, going to be of interest for finding these towers of massive charge towers. Okay. And here, this formula involves the weights in the internal CFT, and then there's some oscillator number, which it doesn't matter what it is, but the details of, say, the spin of this particle will depend on what this number is. Okay. So now we're going to follow our argument in 3 steps. First, we talk about modular invariance. And like I said, this is a review of stuff that was done in 2016, but I'm going to do it maybe more elegantly. We're going to look at the torus partition function of the internal CFT, which has to be modular invariant by assumption, right? That's related to the modular invariance of the one-loop amplitude in the full bosonic string theory. And in particular, if you put in, some primaries, let me write this in cylindrical quantization. The W is W plus 2 pi is W plus 2 pi tau. Then this modular transform just picks up some, instead of getting, a modular invariant, you get some powers of tau out here, tau and tau bar. Okay. What we really want to use to constrain the charge spectrum of this internal CFT is this flavored partition function where I stick in some chemical potentials for my conserved currents. That's the same as inserting a line operator in the spatial direction on this torus, on the A cycle, which is a symmetry operator for these conserved currents. Although I can take my chemical potentials to be complex if I want, that's convenient, and then it's no longer a symmetry operator. Okay. But it's not immediately clear how this flavored partition function with this inserted line operator is going to transform under the S transform, right? Because that's going to turn this line into a line going that way. And that's going to be a twisted sector, right? So it's not going to transform into itself, or at least it won't obviously do that. So if you wanted to use modular invariance to constrain this flavored partition function, you're kind of in a bind. Fortunately, it does turn out to transform into itself up to a factor. So let me first fix my note convention so that the OPEs for my currents have just identity matrices in them. So I'm kind of canonically normalizing my conserved currents. Then you can argue, and I guess there's various papers that do this, but maybe the one that we've relied on is this 2016 paper, that this flavored partition function transforms under a modular transformation in this universal way. It picks up this factor here. Right, if this factor wasn't here, you'd just say it was a, like a modular invariant function. So we actually re-examined this argument because this is kind of an opaque paper in terms of deriving this formula. They also refer to older papers that they say the authors said that they knew this, but then you read the paper and you can't really find it. So we looked at this formula again because we wanted to be sure, and also because we anticipated that we would need to know a little bit more than this to do the superstring. It turns out that this formula can be derived just from this statement about, the modular transformation of these endpoint functions in a pretty simple way. So I want to go through that quickly because it's neat. Basically, you consider two different ways of normal ordering currents on the torus. There's one way where my normal ordering term comes from the Weierstrass P function, and this has very nice modular properties. And there's another way where my normal ordering function is not quite the Weierstrass P function. It's this modified Weierstrass P, where I've added something, a term with the holomorphic Eisenstein series E2. And the reason for adding this term is so that the average of this modified P function over the A cycle of the torus is 0.
I've got a quick dumb question. I'm really rusty on Eisenstein series. Isn't there an issue with convergence in E2? Maybe I'm wrong. It's been a long time since I messed with them.
It does converge, but
Okay.
because, as you say, there is an interesting point about convergence, which is that it's not a modular form.
Okay.
Right? So it's quasi-modular, and that's going to be indeed the whole reason for this.
Okay.
So that's a very interesting point. Yeah, so the interesting properties of E2 are going to play a key role here. So yeah, the sum for the definition of E2, there's a convergent sum, but you can't, it's not absolutely convergent, so you can't change the order of summation. And thus it's not modular, or it's only quasi-modular because of that. Yeah, so good question. So yeah, so this modular normal ordering, so if I consider the modular normal order product of a bunch of currents, well, this is normal ordering, so I'm removing the singularity. So these are analytic functions of W's. The W's are valued on a compact manifold, so that means it's just constant. I can just put them all at the same point. So this is going to be, because of the nice modular properties of the P function, this is going to be a weight n0 modular form. I don't mean to say it's holomorphic, right? It can depend on top R, but it has this transformation of this modular form here. This other normal ordering has a different nice property. So if you look at this, again, these are analytic functions of the W's, so you can put them wherever you want. Or you could also just integrate each of the W's over the A cycle. And when you do that, the integral of one of these J's over the A cycle is precisely the charge operator. So you can change these guys into charge operators. But you got to watch out because of that normal ordering. When you integrate this normal ordered product, you're also going to be integrating the normal ordering pieces. But we designed this modified P function precisely so that its integral over the A cycle was 0. So that means those terms are going to drop out, which they wouldn't have done up here. Okay, so that means we can take this, what I call zero mode normal ordered product, and I can just rewrite it in terms of charge operators, which are the zero modes. That's why I call it that. So that means our flavored partition function is just, I'm suppressing the right movers here for simplicity, is just this torus partition function with this zero mode normal ordered exponential inserted. Okay. Whereas there's a different function where I insert the modular normal ordered exponential. And that thing is a modular form, or a modular function, I should say. Right? That has nice modular properties. So what I need to do to figure out the modular properties of this flavored partition function is to relate these two expressions. And that you can do by some kind of reordering, right? Some re-normal ordering, but you can look up nice formulas for that in Polchinski, for example. So you do this reordering to relate these two guys, and the reordering is going to involve this E2. And then you note that E2 has this funny quasi-modular transformation, right? So it's invariant under tau goes to tau plus 1, but under the tau goes to minus 1 over tau, it has this extra shift here related to that convergence issue that was mentioned earlier. Okay, and so then because of that, so this thing would have not had this factor here, but now this actual flavored partition function gets this extra funny factor here because of precisely this here. And again, I've suppressed the right movers temporarily to change them to save writing. Okay, good. So at this point, I've re-derived that formula that I showed you before, and I've showed you exactly how to derive it. So that's something you could generalize, say, to the superstring. Okay. So now let's apply this. So first of all, I mentioned that I wanted to assume the CFT is compact. What I really want here is that the global symmetries are compact. So instead of, R global symmetries, they're U1 global symmetries, or maybe some non-abelian compact group. What that means is that these chemical potentials are going to have periods, right? So I can add any element of this period lattice to the chemical potentials. This is the dual of the charge lattice, which by the assumption of being compact CFT, this is a discrete lattice as opposed to having a continuum of all real charges. Okay, so I have this period lattice, and that's a period for the chemical potentials. Now I can combine this periodistic condition with the S transform that I worked out up here. So I'm going to do S transform, periodistic condition, S transform. And if I do that, what I end up with is a quasi-periodistic condition where I'm shifting mu not by rho, but by tau times rho. Right? This is why it's convenient to let mu be complex. And instead, now I get this extra factor in front. Okay, so now let me conveniently rewrite my partition function and define h hat, which is like the part of the weight which is not related to the charge. So I have this part coming from the h hat, and then I have this part coming from the charge. And then my chemical potential as before. And you can rewrite your quasi-period condition as this equals this with now q shifted by rho. What that means is that the whole spectrum of the CFT is invariant under shifting my charges by these periods with the h hat and the h hat tilde fixed. Okay, so that's a strong statement, and that's where we're going to get our result from. Let me just quickly make some comments. Right, the charge lattice, which is the dual of this period lattice, is this. And the fact that when you shift the charge lattice by the periods, the spectrum is invariant tells you that the period lattice has to be a sublattice of the charge lattice. Could be equal, but it has to at least be a sublattice. So that means that's the same thing as saying that the period lattice is integral. Likewise, if you look at the T in SL2Z, which means that the difference of H and H tilde, the left and the right looping weights, has to be an integer, you can look at the things that come from this this thing, which you could call spectral flow, come from this shift here, starting with the identity. You get things which are like half rho squared, half rho tilde squared. So these have to have a difference which is an even integer, which means that the period lattice also has to be even. So modular invariance is telling you, incidentally, that this period lattice has to be an even integral lattice. And maybe you're familiar, with this like toroidal compactification situation where this lattice would have been even and unimodular. All right, this is just a weaker statement. It has to be even and integral, but it's related. And you can kind of think about the difference between the charge lattice and the period lattice, where the difference is really a finite group if you take the one quotiented by the other. This finite abelian group is kind of like the analog of a level for the abelian currents. Okay. So starting with the identity of this internal CFT, we're going to get a tower of primaries with these weights here. And that's for every charge QQ tilde in the period lattice. I have to be careful because this lattice doesn't factor into left and right movers. So when I say like this is in the period lattice, I should talk about the pair. Okay. So that's telling me with my dictionary between the internal CFT and the full theory that I have this tower of particles with this mass formula. And this is the thing that we already derived in 2016, although maybe not with the -1. We weren't really thinking about the bosonic string specifically. Other than that refinement, this is something that we knew back in 2016. You get this tower of particles with this mass form. Okay, so the question, as I mentioned before, is whether these things are super extremal or not. So that's going to be the next step, but any questions before I go on to that? Okay.
All good so far.
So as I mentioned in my strategy before, the thing that we want to do to do this check is we want to actually calculate the long-range forces on these particles, and then we're going to use this connection between self-repulsiveness and super extremality that I mentioned before. So let's go now switch modes and talk about computing long-range forces. To do that, the diagrams that contribute to long-range forces are these kind of diagrams like this, where I have this intermediate on-shell force-carrying boson. And since it goes on-shell, that means these really factor into these 3-point amplitudes. So what I need to do to compute long-range forces is just compute 3-point amplitudes between the thing that's having the force on it and the force-carrying bosons, which would be the gauge fields and the graviton and the moduli, or the massless scalars, I should say. Okay. Now, I have to do this on the world sheet, so I'm going to have to represent all these things with vertex operators, and I don't want to have to worry a lot about whether I've normalized my vertex operators correctly. So to do that, I'm going to compare with some other 3-point amplitudes, which will allow me to fix the normalization of the vertex operators. In other words, divide it out, so I don't have to worry about it. So these will be things like the graviton interacting with 2 photons, or the 3 graviton interaction, or the graviton interacting with 2 moduli. Okay. This is kind of like you think about this in EFT as like fixing the kinetic terms for these fields. Okay. So now I can write out what this coefficient of long-range force is. There's one term due to gravity where I just know the answer from EFT, so I'm just normalizing it based on that. And then the other terms here, this is slightly awful looking, but it will simplify. This has to do with the gauge force, and this has to do with the moduli force. And if you examine this expression, you'll see that normalization of every single vertex operator cancels out of this expression. So you don't have to worry about normalizing them correctly. That was the goal of doing this. And I'm also dropping things that depend on the momentum and the polarizations and all that. I'm not being careful about those things. Maybe you should be careful, but what I'm going to do is I'm not going to compute them. Instead, I'm going to observe that these only depend on the external part of the CFD, which is free bosons. This is the same for any bosonic string theory, at least it only depends on the dimension, right? So what I want to do is I want to look at everything that depends on the theory, the internal CFD part, and compute those things. And then all the stuff that doesn't depend on the theory, I only need to compute it once. So what I'm going to do is I'm going to compute all that stuff by looking at a particular example, which is going to be bosonic string theory on a torus, which is worked out in an appendix of our paper. I won't even show you the details, but you can go and look there if you want. And so by normalizing with that particular example, I can fix all those momentum-dependent, polarization-dependent factors, and I don't have to compute them. So I only really have to care about the part that does depend on which theory I'm in. Okay. So let's focus on the internal CFD part. And okay, it's pretty trivial to show that the dilaton is special and it doesn't mix up with the other massless scalars. So the dilaton and the graviton are both coming from the identity operator in the internal CFT. So that just means they're completely universal. And you can go and look at an example and compute those contributions. Easy enough. So I didn't have to do any work for that. Now let's look at the gauge contribution. You can reduce all that stuff I wrote before to stuff involving the internal CFD. And that's going to look like this. Here, J is just a notation for both the left and the right currents. And then you can further rewrite these 3-point functions as matrix elements of operators, or just, overlaps of 2 kets. That's kind of a trivial manipulation, again, up to maybe factors of Z that are going to be universal. Okay. And then you can check these kinds of overlaps between 2 J's, given the way that I normalize the OPEs, these are just delta functions. Okay, you can actually compute this. This is an honest calculation. And then, okay, so the other things you need to calculate are things with psi and the J in the middle. And then by conformal invariance, that goes like 1 over Z. And so you compute the integral of this, with the integral around the origin. That gives you the charge. That's easy to compute. So that fixes what this thing is. Okay. And you can do the same thing for the right moving currents. So what that tells you is that overall the gauge component, the gauge part of the force, no surprise, is going to involve the q dot q prime for, say, two particles, q and q prime. And that's the left moving part, and this is the right moving part. And maybe in principle, these are different numbers because I didn't carefully compute, the z's and the z bars. I threw them into these factors. Okay. But then you go to compare an example and you figure out exactly what those prefactors are. And they're indeed very simple. They're just numbers. And you get this answer here. Okay. So by doing this, detailed calculation for the things that actually depend on what internal CFT you have, and then normalizing with this bosonic string theory example, you fix this answer here. Okay, so we've got the gauge force, we've got the graviton and the dilaton. Now we just need to deal with the moduli. And as I mentioned before, that's going to be the most non-trivial part. So we do the same kind of thing for the moduli. We observe that a subset, or I should say massless scalars, really. A subset of these massless scalars are these JJ bar moduli. They're built from the product of a left moving current and a right moving current. Okay, you can easily find their 2-point function using the OPEs again. Now let me think about some other 1-1 primary, which is neutral. If it was a charged 1-1 primary, it would not contribute to the long range force. So I don't need to think about those. So let me consider some other neutral 1-1 primary, which is not one of these JJ bar moduli. I need to allow for such things. Those could be like some complicated moduli of a Calabi-Yau manifold or something. Okay, first of all, I could require, just by a choice of basis, that these are orthogonal to my JJ bar moduli. Right? I can just shift these guys by JJ bar moduli to make this true. Okay, so if you impose this condition, what you find is that the combination of these, current lowering operators, these are coming from the modes of the currents on chi is 0, which turns out to imply that they're both individually annihilate this state, which, because this is just, weight 1, it's the same as saying that all of the lowering and 0 mode operators for the current annihilate this state. The 0 mode is because it's annihilated because it's neutral. This is what you might call a current primary, which is also neutral. Right? It's annihilated by all the lowering operators coming from the conserved currents. Okay. So we're going to use that property in a minute. So the thing we wanted to compute was the matrix element, the psi matrix element of these 1-1 operators. So for these JJ bar ones, we just use a similar calculation to what I showed you above, and you get this contribution. This is again an honest calculation with an equal sign. Okay, we still need to compute this one with this chi. And now you might be a little worried because I didn't tell you much about chi, right? I just told you it's not one of the JJ bar moduli, it's orthogonal to them. Well, okay, what could it possibly be in a way if it's not going to depend on the details of the theory? Well, it turns out it's 0, right? So we have to show that it's 0. That's kind of the only possible universal answer. So we use something called the Sugawara construction, which allows us to split the stress tensor into 2 pieces. One piece is a piece that's associated to the currents, and one is the other piece is everything that's left over. And the piece associated to the currents, so here I'm using like a normal ordering. I mentioned some normal orderings on the torus before. Here I'm just doing normal ordering in the plane. So then just subtracting like a 1 over z squared. This is like a conformal normal ordering in the language of Polchinski. Okay. So when I do this, the magic is that I get 2 decoupled Virasoro algebras, one for the TJ and one for the T hat. And the central charges of the current things depends on how many currents you have of left and right type. And the other part is just what's left over. Okay. So now let's think about these charged states that I constructed using my modular invariance argument. So you can find what their weights are under this this J part. This is a straightforward, I omitted one equality in the middle, but you get 1/2 q squared. So the weights under the J part are actually their total weights. So their weights under the remaining part are 0. It's kind of like it only transforms under the J part of the stress tensor and not under the remaining part. Whereas for this chi field, you get the opposite situation. It has no weight under the J part, and the entire weight is under the other T hat part. Okay. Here it was important that this is neutral. This is also, by the way, also a current primary, but because of its charge, you get this contribution here. Okay, so this thing is what we wanted to compute, this 3-point function. And this is constrained by conformal invariance, both for the Tj and separately for the T hat. So we split up the stress tensor. Each thing has its own conformal symmetry now. Okay. But in terms of T hat, this looks like a 1-point function, right? Because this is 0 weight, so it's like the identity as far as T hat is concerned. Same thing here. Only this has weight 1, 1. So if you have a 1-point function of something in non-zero weight, conformal invariance just tells you it has to be 0. So that's telling you that this should be 0. Okay. I have another argument of the same thing if you guys want to see it, or should I skip that?
No strong opinion, whichever you prefer.
Maybe I'll quickly sketch it. It's basically it's another way of, if you got a little concerned about like, oh, do I know that I really have this separate conformal invariance? Another way to do this is just sort of more straightforward. You take the fact that this has weight 1 under your L hat, you write this in path integral language and radial quantization as, integrating T around here to make L naught applied to chi being equal to chi. And then you move this in the Z plane. You have this translational invariance that you can use. And now you deform the integration contour so that instead of having this loop around this point, you have 2 loops, one inside and one outside. And I should say that something else might be at the origin, so I didn't want to pass through the origin when I did this. I didn't have to. Okay, but now again, we're in radial quantization. And so the time ordering means that, one of these is inserted after that and one's inserted before. So I'm going to end up with a commutator, right? It's the sum of this integral and that integral. So I'm going to get the commutator. And the thing that shows up in here is just L naught and L hat naught and Z L hat minus 1. Okay. So you can rewrite this thing with this commutator. And now when you have L hat naught or L hat minus 1 acting on psi, you can show that they annihilate it. And similarly, L hat minus 1 acting to the left on psi is the same as L hat plus 1 acting on psi. All of these things annihilate it, and that's because it has weight 0 under this L hat part. It's like the standard statement that the vacuum is annihilated by L0 plus and L plus and minus 1. You can prove it. I'm not just appealing to that. You can prove it, but it's the same argument as before. Okay, so once again, this thing is 0. Okay, so that was a crucial step that, although you can have lots of other moduli, they don't couple to these particular tower particles that you constructed by modular invariance. So maybe, I don't know if that answers your question, Eric, about moduli from way back in the talk.
Yeah, I guess the answer I'm taking is that you're taking a purely CFT based approach to the problem. I mean, the way you're not approaching it from the question of you've got you're not approaching it from a geometric perspective. You're approaching it from a purely CFT perspective. You sort of wrapped up all the questions about the moduli in terms of some abstract CFT computation, which is great. It completely resolves the issue, or at least for this, I'm still a bit curious about. I'm still curious about geometric moduli dependence, but for completely independent reasons, which are not relevant to your talk. I'll put it like that.
Yeah. So the motivation for doing this is that then we can cover not even just all the geometric cases, but even non-geometric cases at the same time.
Yeah, that's completely fair.
Okay. So in the end, the only contribution to the only moduli contribution to the force is coming from these JJ bar moduli. I showed you what those terms look like, and so you find it's proportional to these things. Like this is q dot q prime, q tilde dot q tilde prime. And then you again fix the normalization by comparing with the example of bosonic string theory on a torus, and you get this nice formula, a relatively nice formula. Notice there's, factors of m showing up here. So it's not just a constant anymore, this extra factor, but it's something that depends on the momentum. Okay. So if you put all these pieces together, we computed the 3 contributions to the force, you put them all together, and kind of miraculously, they factor in this interesting way. By the way, the same formula applies to heterotic string theory on a torus. And I think, our next paper will be showing that this applies to any heterotic string theory, but of course we haven't finished that paper yet. Okay. So we have this interesting factorized formula. We're interested in when are these particles self-repulsive. So when is this positive or 0? And that happens precisely when alpha prime over 4m squared is sandwiched in between half q squared and half q tilde squared in either order. Because basically either one of these terms is 0, or you want these two terms to have opposite signs, and so that you get a plus here. That's the only way to get this self-repulsive. Okay, and if you recall the spectrum I wrote for you before, and there's this number of oscillators here, when there's 0 oscillators, it's kind of complicated when you get self-repulsive or not. When there's 1 oscillator, you always get self-repulsive, or 0 in fact. And when there's more than 1, you always get self-attractive. So for the 0 case, let me mention, right, if the difference between q and q tilde squared is bigger than 2, then you get this is strictly self-repulsive. If it's equal to 2, you get 0 long-range self-force. And when it's equal to, when their q and q tilde squared are equal, alpha prime over 4m squared lies below both of these, right? It's, so, you get, these things are both negative, right? So negative times negative, positive, so you still get something which is self-attractive in that case. Okay, but it doesn't matter because for n equals 1, you always get something which has f equals 0, so there's at least one self-repulsive particle for every charge. So we can, I guess I rewrote something here, you can ignore this. We now have, for every charge, we have these particles which have, in fact, 0 long-range self-force. And so I can plug that into the argument I showed you before to show that indeed this is the extremality event. Because I'm looking at these particles with n equals 1, which have this mass here. Okay.
Very good.
So the lightest things which have a -1 here, your bosonic string tachyon is being friendly here. These things are strictly super extremal. So this proves the sublattice weak gravity conjecture, and in particular the Aguryev-Offa version, where you only get to saturate the bound if you're BPS, and none of these things are BPS, so they don't saturate. So that's it. I'd be happy to talk about comments, follow-ups, etc. But I think since I've gotten to the end of my time anyway, this is a good place to stop.
Thank you. Any questions?
Not a question, just a comment. It was a very nice talk. Thank you for speaking here. If I'm tempted to ask what would the next step be, but I think you've already addressed it. You said you're thinking about type 2 strings and heterotic strings. Let me ask a vaguer question. You've given a purely CFT-based method of deriving the relevant form of the weak gravity conjecture. Can you, my vague question is there, sorry, I haven't quite formulated my vague question yet. I'm trying to build up in my head. Is there, I guess, now that you have a proof, does that give you any thoughts as to a more, I think I want to say a more insight. This doesn't quite sound right. So does it give you any way of, does it give you any alternative insights, any alternative ways to think about the weak gravity conjecture, any alternative approaches to it? I mean, you've derived it. That's great. That's fantastic. From a purely CFT-based method, does that Yeah, sorry, it's a vague question. I don't think I have anything specific to ask.
I mean, it supports these kind of pretty strong versions of the weak gravity conjecture, and maybe that's notable. It also supports this Guryev-Alpha version, right, where you should only saturate the conjecture when you're BPS. And those things didn't have to happen.
Fair
And
enough.
even this about the Guryev-Alpha version, I'm not yet sure if it does happen for the superstring because we haven't
Okay.
finished it yet. So that's going to be very interesting to find out if it does. Maybe, most of the argument I can kind of see how it's going to work, but that's one where I have to do it all out before I see what happens.
What about cases like, for example, an F-theory compactification, where I may not necessarily know how to construct the theory, how to describe the theory in a completely perturbative fashion? So
Yes.
as I understand it, your arguments are valid for cases where just a good old-fashioned ordinary string compactification. You have a CFT, you've got some, a flat space.
As
What
long as
about
it's perturbative in the string coupling, then the argument is valid for that electric NSNS sector.
yeah.
So if you wanted to do something non-perturbative, of course, you can't do this,
Indeed.
but you can take some perturbative result, and if you're talking about BPS particles, you could extrapolate that.
Okay.
Use a wall crossing argument or something, right?
And certainly knowing this case, this is an extremely strong, this is a really strong argument. So that's all good too. Okay.
I hope that maybe like in the type 2 string theory case that something can be done about like RR charges, for example, right? Maybe you study boundary conditions, right? And thus you learn what the D-branes are. And
Fair
the
enough.
D-branes are things that are charged, right? So that I don't know if that works, but that's in terms of vaguer, longer term follow-ups, that's something that I have in my mind.
Fair enough. Sounds good.
Yeah, I have a question then. So you mentioned this the connection from this weak gravity conjecture to the no global symmetry conjecture. So I mean another conjecture which is closely related is the cobordism one. So do you have any thought or like comments? Is there any worldsheet perspective we can take to say something about the cobordism conjecture? Because as far as I know previously, basically the cobordism conjecture is still like more or less based on the space-time discussion.
Right. So I know the cobordism conjecture sometimes hinges on the existence of certain, objects, right? And maybe
Yes, right. Like if you want to trivialize those things, then in space-time you have to have certain type of defect to,
so maybe you could
trivialize the cobordism class.
that kind of like I said about studying boundary conditions. Maybe you could believe that a powerful string theory argument could construct some of the objects that you want if they happen to be things that are easily accessible to a perturbative string, like a D-brane.
I see. Okay.
It's a pretty far out speculation because that's not what I did in this talk at all, but
Yeah, I understand. Yeah,
the kind
I
of thing
see.
I could imagine maybe. And something else I'm quite interested in, but I just don't know what to do, is the distance conjecture. And, can one do anything with perturbative string theory and the distance conjecture? It's a question. I can tell you what the question is, right? It's a question about like the exactly marginal operators in the CFT and how they affect the spectrum, but it's not a question that I immediately know how to answer.
Yeah, I understand. I see. Okay, thanks.
Mhm.
Any other questions? Yeah, if no, let's thank Ben again.
Thanks
Very
again.
nice talk. Thanks.
Thank you for the talk.